Welcome to homework.
Hello everyone, today we're doing chapter 11, problem 18, and this problem asks us, using these following reagents, how would we prepare this final product here? Show all your reagents and curved arrow or curly arrow mechanisms to show the movement of electrons. So this is kind of like a retrosynthesis problem, but we're given all the information we need, so we just need to show the mechanism. So identifying the products, we need to break up the product into different components of that we're allowed to start with. So obviously, the double bond is most likely going to originate from the triple bond. So we know that the double bond is from the triple bond. We see that we have kind of this 1, 2, 3, 4, 5 carbon structure or substituent on this side of the carbon, a double bond on the right side of the double bond. And we see that we're starting off with a 1, 2, 3, 4, 5 carbon alkyl halide, which is actually going to act as our electrophile somehow. So we know that eventually we need to make this kick off the bromine to form this entire side of our molecule here. So we know that this corresponds to this entire section here, leaving us these 2 carbons with this 2 carbon alkyl halide over here. So obviously, combining these 2 alkyl halides together is your central alkyne. So let's use the alkyne to first add one of these substituents, and arbitrarily I'll just choose this green one here. So I'll use my alkyne, and now I need to make this alkyne into a nucleophile so it can nucleophilically attack this carbon and kick off the bromine. And we know that obviously this is going to be the nucleophile, not this, because this has a leaving group on it. So your electrophile is going to be the molecule that has your leaving group on it. So we know that in previous examples, if I add something like sodium hydride will abstract one of these protons, making a carb anion. So we know that we'll fully draw our mechanism. The hydride would abstract one of these protons, making a bond. When you make a bond, you break a bond, so those 2 electrons of the sigma bond will go onto the carbon nucleus as shown here, and will form hydrogen gas, which will just dissipate from the reaction vessel. And now that's step 1. Step 2, if I add my reagent, I know that the 2 electrons on the carbon being very reactive can act as a nucleophile and do an SN2 considered 1-step mech to kick off our leaving group and form this intermediate. So counter carbons, we have 1, 2, 3, 4, 5. Now we're left with this plus a bromide anion. So now we know that we need to somehow the product actually is a triple bond, not a double bond. Sorry, I misread that. So that actually makes it easier for us. So this is very good. So we don't have to use any poisoned catalyst to reduce a triple bond to a double bond, but not any further. So I'm sure that'll be taught in later chapters. But if you use some sort of Lindlar's catalyst, it's called, you'll be able to reduce an alkyne to an alkene without going fully down to an alkane. So that's what I was going to suggest. But because the product has an alkyne, it just makes our lives easier. So now we need to make this side of the alkyne a nucleophile again, so we can nucleophilically attack this electrophile. So once again, I'm just going to use the same reagents, number 1 being sodium hydride, number 2 being my alkyl halide. Sodium hydride being H- is going to pick up that proton, making a bond. You make a bond, you break a bond, so those 2 electrons are going to go onto the carbon nucleus to form our carbon anion. And now carbon anion is now very reactive, very electron rich, so it's going to act as a nucleophile to go through an SN2 considered 1-step mechanism, 180-degree backside nucleophilic attack, to form now what is going to be our final product. Plus, don't forget all your side reagents. We have H2 gas, and we're going to have NaBr, sodium bromide as a salt being formed here as well, and we're left with our final product.